I would like to make a disclaimer. I know we're on a school of formalized mathematics, but of course I like to come out against what everybody thinks is a basic assumption of life, namely that verification of proofs, math proofs, is a good thing. I also think it's a good thing, but there are some problems to this assumption. One is that you need to do full formalization. We've seen it, right? Yes, you can use sorry, but that's kind of a cheat of saying, I will do it later. And it doesn't quite do what mathematicians do, namely offload, it was talked about earlier, offload a lot of the work to your reader. And most of what math does is actually doing exactly this, trusting on the fact that we have an intelligent person on the other side of communication, and that allows us to transport a huge amount of knowledge down an extremely narrow channel. Right? And formality may not be actually the right channel. It's basically, I believe, that verifying something like the odd order theorem gives you could say one bit of information. But of course, we knew that the odd order theorem is actually true by other means, reviewing and so on, and lots of grad students looking at it. So you could say that is probably only 0.001 bit of information that we're gaining from the whole thing. Of course, I'm overstating this a little bit, because formalization enables a lot of good things. It's kind of like the Saturn rockets when people wanted to go to the moon. They gave us a lot of good things. Many people say that verification came out of the Saturn rockets. Most people only know about the Teflon pans. But of course, if you want verification, you shouldn't really try to put people on the moon for that, right? And so is formalization really what we want? Can we do with less? Because one of the things that being in a school here, where we kind of spend a week on teaching people formalization who already know math, so you've all went through the kind of brainwashing of thinking deep and rigorously already, and we still have to prove to show how you do formalized math. So there's something that's very, very expensive, and can we kind of do with less? And I feel justified by this title, Prospects of Formalized Mathematics, that we chose, to say, well, maybe formalization is not just verifying Kepler's conjecture and those kind of things. Can we do all the good stuff that's certainly happening with less? And just to go towards an answer, I would like to kind of go and look at what's done in math and in formal mathematics. And one thing I think we have to state is, if you look out there, LaTeX is the standard of writing math. You could argue that it's actually blackboards or green boards, but I think if we can at least accept that. So TeX, the basis of LaTeX, was actually conceived for typesetting mathematical formulae. TeX-like syntax is so good that we're using it everywhere. We write it down in Markdown, we write email with $ something or the other, and relying on our highly intelligent reader who have a built-in TeX parser and typesetter in their brains. Ephemeral formulae, right? Scientific publishing uses it extensively, and if you come with a word paper, you're kind of looked at a bit like that, right? But of course, there are problems here. It's only for layout. It's basically describing how to put dots of ink on static fixed width pages. That's what it's for. And if you think about the web that we all use all the time, that's not static fixed pages, but we want to be able to read our math on slightly different formats, right? In the comfort of our beach and those kind of things, where we don't have the paper with us. All of those things LaTeX is not very good at. So if we think about what math communication is really for, which is kind of the transportation of knowledge from brains to brains, we do not need dead trees in the middle. There might be things that can do better than dead trees for that. And obviously, all of us are going to think, well, why is he telling me all this? Well, come on, let's do it in lean. Right? Formal mathematics is out there, and so why don't we kind of use formalized mathematics for all of our things? Well, it clashes what we are teaching our students traditionally. Right? We're using blackboards, and we have a highly evolved formula language, and we have LaTeX that makes it readable and writable. And very often, we actually want the qualities of natural language in there. Natural language is very flexible. Natural language deals beautifully with our ideas being a bit fuzzy, with our proofs being wrong 99% of the time, and if we're lucky, they're correct when we submit. If we're slightly less lucky, they're actually correct when we publish, and sometimes not even that, right? So there is something for informal mathematics, for development, and we're doing it all the time. Right, with Fermat's last theorem, but also with the Kepler conjecture. The first stages of these monumental proofs are as LaTeX documents, later cross-referenced with the formal stuff, but people, for onboarding new students or colleagues, all of these things need to do that. And one thing I would like to say is formalized mathematics is difficult to learn and takes a huge investment. And if you're saying, no, but that's not the case in Lean 4, you don't get to say that because you're already brainwashed. Let me show you, right? The real math is in any right triangle with sides A, B, and C, and the right angle opposite to C, the equation a squared plus b squared equals c squared holds. That's what you might have seen in school or in undergrad math or something like this. And if you have any of the systems we're talking about, it looks slightly different. Right? And I'm sure even you, as brainwashed formalized mathematics people, can see the difference. If not, there's doctors to that. Right? But the question is, what do we need from this? And I would claim that we don't need the full formality. In particular, what these systems are all geared towards is this one bit of information saying, this is true. Kohlhase, we have a proof. Right? We're not worried about that, really. Very few people were really worried that the Kepler conjecture might be wrong. The liquid tensor experiment is a different case, right? But that's kind of also pre-published math, it was. So I would claim that there's different levels of formality, if you think about it. And very often we can do a lot with less formality. In particular, the thing that we need is not so much this information, boing, this is actually true. We typically know that, know the things to be true, except in computer science where things are so weird and wonderful that you may actually forget one of the 75 cases and only look at 74. So if you are actually looking at banking protocols, it's good that we have verification. But in math, that's typically not the case. We have a good intuition. We humans are good at this. Right? So I would claim we often need a little bit more help. A little bit more help with reading all these things that we're reading. Where we're not sure, what was plurisubharmonic again? Are there any edge cases I'm forgetting? I know I learned about plurisubharmonic in my complex analysis class, but that's, for me personally, almost 40 years back, so I don't quite have it in my mind. So, we might actually want to see whether something is a typo or a feature, right? Which means something like type checking might help, but we often, very often, have all these things where we don't quite know what they mean. They might even be informal, intentionally so. So we might really want to see, if we see something like this, we want to know, is this the complex unit, the I, or is it actually a variable? And just this distinction, this is a variable and it's declared over there. Right, there's a function here which we don't really know a lot about. Is it just one or for every, right? Is this the tensor product or something that my paper weirdly overdefined locally, stuff like that. So we would, I claim, some things like that might actually be enough. And note, one of the things that's not on the slide is valid or correct or all of those things. Right? But only kind of more structural properties, disambiguation, what does it mean, where is it defined, all these kind of things. And what I want to get you thinking about is this true, or is Kohlhase just imagining this? And what might be the applications? And I want to show you a couple of diagrams that I've fallen in love with. Most people in this room, otherwise you wouldn't be here, you would probably say, well, almost all of the documents, this is the number of documents against the level of formality, somewhere fall into the very informal category, right? Even with what I saw 77,000 definitions in MathLib, it's kind of a tiny number compared to 120,000 pure math papers we have a year, right? We're not winning the way, the formalization race is not being won at the moment. Right? And most people would say, oh, but wouldn't it be nice to have a curve like this, where everything is formal and we kind of have achieved world domination and we can do all the nice Teflon plans. But if you look at what would have to happen here, is kind of you need to have a big jump. If we could convert all the CS students and all of the math students to be in this room and work diligently for 3 years, then we might get somewhere here in 1 year and maybe there in 20 years, but we don't know whether it's worth it. Okay, because math would stop, essentially, if we did that. And so, wouldn't it be much nicer if we kind of take this blue line, which is the current distribution, and kind of step by step by step by step would formalize things bit by bit. And kind of come up, instead of this way, where everything is formal, we don't need formalized emails. We don't need formalized idea sessions on Blackboard, right? Kind of come up with this distribution of documents. But of course that's a problem, right? If formality is an all or nothing thing, then kind of these things in between don't exist. So I believe that we should have ways of coming up with these intermediate steps. Make formalization something in system rather than out system, like here. And that's one thing I believe that all proof of systems actually suffer from. They're trying to get by with tooling, but I think that should be part of our science. Another thing, if you think about all the services you're getting, the Teflon pans, and all of the systems kind of have things like proof checking, proof search, also called automation, but also change management, which is often in the tooling, semantic search, math search, and those kind of things. Most systems have that, and it's great to have formalization for it. But if you think about the degree of formalization you have to do to get some kind of functionality, proof checking is actually the worst. You have to have a fully formal proof, and at the end it runs through and you get functionality, namely it's safe. Somehow, counterintuitively, proof search, automation, has a better characteristic, right? I think all of you agree is that these are the bad ones, those are the good ones. It's also that these are the ones we humans are good at. We are really good with our intuition of burying very deep into a specific small problem and solving it. Whereas things like search, math search, we are terrible at. Right? Nobody of you knows about the 120,000 papers that came out last year. You've read 10, 15, if you're good. Right. Something, that's where we need help. This is what everybody here is talking about. Something is wrong here, I think. And now if you this is what I think of as a bang for the buck thing, right? When you kind of map the investment against the return, then we're seeing things like the web, which took up like crazy. Why? Because there's more return than investment. It's above this line. Lean, Isabel, and so on are kind of like here. Humongous investment, sometimes outside of math, really big return. Think of verifying Intel chips. Think of verifying programs and so on, right? I think there must be something in the middle where we have a medium investment and medium return. LaTeX is somewhere here. That doesn't quite exist. MathML might be here. It's terrible in terms of investment. We really want to move it over here somewhere. HTML, MathML, those kind of things. There's a couple of things. When I think of reimagining things, I always think of this as kind of analogous to taking your motorbike, disassembling it, and reassembling. And then typically, or at least if you're as good with motorcycles as I am, there are some leftover parts and some of them are missing after reassembling. And that's the interesting information. So what are the superfluous parts and what are the missing parts? I think one of the superfluous parts in this is actually truth or validity or correctness. The kind of missing parts are the big scale helping people with horizontal problems like search. My main thing I think I would like to keep in the reassembled motorbike is modularity and what we call theory graphs. I'm not going to go into this at all, but I'm going to show you sTeX, which is our experiment of actually taking LaTeX and making it a little bit halfway to formal methods. Yeah.
Are there references for that section you skipped?
I'll make it available. You can always come into my to the afternoon sessions, and I'll be very happy to talk to you about those things whenever. Okay, so sTeX
So guessing what you're talking about, like in graph theory, one of the biggest issues with formalization is that there's 30 different representation of what a graph means.
Yes.
And then if someone uses the word graph in a piece of paper, it might mean different from what.
Absolutely, and that's really what these theory graphs are all about. And it's not the big problem in formalization because most systems have some kind of this. But if you think of this as an ontology, ontology people always have the problem with data integration, right? Is the proton decay 10 to the 14 years or 10 to the 16 years, and you get different physics, right? If instead of having one big ontology, you have swarms of little ontologies that have lots of inheritance between them, then it's no problem. You have a theory here that actually says 10 to the 14, and a theory there that is 10 to the 16, and they share almost all of the physics, but then you can make this your home theory, or not your home theory, and if you're lucky, there's kind of truth-preserving mappings between those things. And that's why I like modularity so much. It gets rid of a lot of problems. So one of the main things sTeX does is it does all the things that theory graphs allow you to do. So we have a LaTeX package, which allows you to embed, in a way you can say, invisible semantic annotations. Invisible semantic annotations that turn a LaTeX paper as you know it into something like this. So how does that work? We write things like SymDecal. We make LaTeX macros that are semantic, that are mathematical. Not just write something, make ink on paper, but also give us a way of parsing in an unambiguous way what we're seeing. We're writing, instead of A plus B plus C, we're writing something like nat plus ABC. We're writing theories by begin S module and then a name, right? We saw it in PVS very nicely. We had these theories and they had interpretation and they had imports and they had all kinds of things. The arrows in the theory graph. And we can do that via what we call use modules or import modules or those kind of things. And these, these modules are actually libraries like we know them, highly engineered, very well tested libraries that anybody can just use and actually have the documentation, the mathematical documentation coming around with it. We're changing LaTeX to object-oriented LaTeX, essentially. We have notations and all of those kind of things. The last thing I want to say is when you write sTeX, you can do one of two things. You can run PDF LaTeX over it. It's part of TeX Live, so it's on your computer already. And it gives you natural-looking PDFs, if you do everything right. And when I mean it, it's not the natural-looking that you get from Isabelle or Lean or something like this, but regular LaTeX. What you can also do is you can run it through a new program called RustTeX, which is a TeX re-implementation, which instead of making PDF, actually makes nice HTML. If you apply it to sTeX, it gives you sHTML, semantically annotated HTML, which actually can be used to harvest into theorem provers. Of course, okay, went away. If you compare it to a theory graph like this, which has all these formal parts like, oh, composition is associative in semigroups, you would have English here instead. It would be partially opaque to a theorem prover, which means the theorem prover cannot do what it's designed for, namely prove and say, Kohlhase, we have a proof. But we can still do all the Teflon pan work. We can search for it. We're interested in interesting theorems, whether they're true or not. We can determine those things with other means. We can actually show people, we can do this on our students and give them help in learning. We can use all of these flexi-formal things to give them the right problems for self-study at the right time, which is the ALeA system I'm not showing you. But of course, I will actually show you the system and how it exactly works based on flexiformalism. So the take-home message here really is, let's rethink whether formalization is always what we want. Maybe we may need to develop the tooling without the assumption that it's for the one bit of verifying a theorem. Verifying math works very well. It's not broken, thank you very much. Right? Math theorems can be in two states. Either they're irrelevant and nobody reads them, so it's completely irrelevant whether they're correct or not, or they're really relevant and useful, then we have grad students. And we don't need Isabel and Lean and those kind of things just for verifying them. Yeah, thanks a lot.